Hello, I am Tim Lichtenberg from the University of Oxford, where I am working on the physical and chemical processes that shape rocky, potentially habitable worlds during their formation and early evolution. In this talk, I will review and introduce some aspects of the journey of rocky planets from their birthplace in the interstellar medium during star formation to the magma ocean phase that allows them to solidify and host the earliest surface environments that potentially give rise to life. I will qualitatively introduce many processes and important mechanisms that profoundly shape the build-up and composition of habitable planets. How planets then evolve, depending on the composition they acquire during their formation, will be discussed by Francis Nemo in the accompanying talk during the conference. Because I necessarily need to simplify and leave out some aspects, where possible, I refer to topical reviews that are labeled in blue in one of the slide corners. Let us begin with our own home planetary system, the only one that we knew until about 25 years ago. The solar system has a peculiar structure, with 4 small, rocky, and mostly dry planets on the inside, and larger and wetter planets on the outside. The solar system was for a long time the only planetary system that we could study, and it still is our best source of information on the physical and chemical processes that shape planets. This is in particular true for rock-dominated planets that may be similar to Earth, the only life-harboring world we know until today. Because of this, most of the mechanisms I will discuss today are rooted in observations of the solar system, but I will discuss them in a general fashion that aims to relate the timescales and processes to a general understanding of what shapes potentially habitable worlds in exoplanetary systems. During the course of the exoplanet revolution until today, it changed our view, and we are finally not confined anymore to a single planetary system, and we can instead start to compare to other extrasolar planets with our own. However, this turns out to be quite demanding. Let me demonstrate this with a view of diversity and bulk density of known extrasolar planets until 2017, with known uncertainties and below about 4 Earth radii and 25 Earth masses. Earth is down here. The closer to the pure hydrogen-helium composition isoline, planets are generally more gassy. Down to the pure iron isoline, planets become more Mercury-like, with large metal cores. In between, it is a mix of gas, iron, rock, and volatile ices. For instance, Ganymede in our own solar system presents such a mix of all these ingredients: an iron core and a rocky mantle that is overlain by a volatile ice carapace and a liquid fluid layer. From an exoplanet point of view, the question really is, how much can the composition of a planet really deviate from the tiny, quite confined compositional point of the Earth in order to still count as habitable? To illustrate the severity of this problem, let's look at the right side here. The Earth features about 0.1 weight% of water, which, cosmochemically speaking, is just a tiny fraction. For instance, comets have a volatile ice fraction of several tenths of weight%. Even carbonaceous chondrite meteorites from the outer solar system still host up to several weight% of water by mass. If you add just 1 weight% of water to the Earth mantle, you end up as a super Ganymede. The rocky mantle and atmosphere of such a planet are isolated from one another and cannot equilibrate. To first order, these planets are doomed to being frozen forever or evolve toward catastrophic runaway greenhouse climates. Because of this importance of the relative ratio of rock to volatiles, here simply ices, in the remainder of this talk and throughout Francis' talk, we will focus on the fate of planets within that phase space here. From rock that makes up planetary mantles, to volatile ices like water, to core-forming metal. You see that the rocky planets of the solar system span a large range in the metal rock space, where the moons span nearly the complete range in ice metal space. Because the actual rock-metal ratio is unknown for the icy moons, they may in fact span a large portion of this rock-to-metal-to-ice parameter space. In order to set these trends in context, I will chart the evolution of planets from their early accretion during the star formation process itself to until cooldown of the magma ocean phase, subsequent to primary planetary accretion. Specifically, Perhaps slightly deviating from what is usually emphasized in astronomy-inclined presentations, it will highlight the geophysical and compositional evolution of the matter and building blocks that form the planets. This evolution and the chemical and physical processes shape the fate of fully fledged planets and the environmental context in which prebiotic chemists aim to unravel the origins of life. We do not know the planetary context of the earliest Earth itself, and therefore our understanding of how physics and chemistry from which life can emerge remain clouded. Extrasolar planets open a window of opportunity to better constrain and understand the diversity of these environments, and therefore will help us better understand ourselves. So, even though disconnected at first glance, there's a direct line of inquiry that stretches from the diversity of planetary environments in our own galaxy to the onset and earliest life on the Hadean Earth. As indicated, let us start with our own planets. Was the formation of the solar system special, or rather the cosmic norm? From by now more than 100 years of research, we were able to establish a remarkable chronology of the earliest planetary materials in the accreting solar system that inform us how the archetypes of habitable planets, the terrestrial planets of our own solar system, formed. The left-hand side shows the onset of our solar system timeline, the earliest known solids, calcium aluminum-rich inclusions, which are shortly followed by accretion of planetesimals that we today measure in the form of iron meteorites, and later the formation of more pristine materials, chondrites. Mars and probably the terrestrial protoplanets accreted to embryo sizes within the lifetime of the circumstellar disk, which lived about 4 to 5 million years. This defines the early stage of accretion, when most of the material was locked in dust grains in smaller bodies. Over time, these grew to larger objects, which defines the later stage of planetary accretion, which is dominated by larger and larger impacts between growing protoplanets. These impacts then drastically melted and reshaped the structure and composition of the protoplanets from the earliest formation phase. The result of this can be alien worlds that are desiccated, or instead emerge as habitable worlds. These two stages roughly define the outline of the rest of this talk, where we'll start with the early phase, starting from the star formation process itself, and then go in the direction of the last formation stages, solidification of the planet and establishment of the earliest atmosphere. Here you see on top an illustration, and below astronomical images of the formation stages of planetary systems. In the interstellar medium, in molecular cloud cores, matter clumps together and compresses under angular momentum conservation to form a protostellar disk. While still actively accreting, these systems live in the order of a few 100,000 years, after which the disk becomes disconnected from the surrounding medium and evolves and disperses isolated. After a few million years, the disk vanishes and a young planetary system emerges, in which the last, final stages of protoplanet accretion play out. At the onset of planetary systems formation, the astrochemically derived inventory of pristine solids that contribute to the planet formation process are shown here. Oxygen is mostly in silicates, water and CO2 and CO, but a large fraction is locked in unknown carriers. The carbon budget is dominated by refractory compounds, for instance graphite and CO. Nitrogen is a mystery, with ammonium refractories again being a major reservoir, but the largest nitrogen carrier is currently unknown. It may be N2. These are the inherited compositions of solids from before the planet formation process that feed the disk. However, starting with the disk stage, these inventories can be reset during planet formation. This is a long-standing debate between the inheritance and reset scenario that we unfortunately won't be able to completely demystify today, but we will discuss some mechanisms that may crucially influence the fraction of materials that contribute unaltered to planets or are processed during planetary accretion. In any case, beginning from the protostellar disk phase, volatile ices that are carried by grains stream onto the disk. Depending on the evolutionary stage of the disk, it can be hotter or colder, but generally is hotter toward the protostar. Inside of about 100 Kelvin, most of the chemistry that is derived from the interstellar medium becomes reset due to sublimation processes inside the centrifugal barrier, which defines the region where the material flow from viscous disk evolution changes its direction. Outflows from jets can further contribute to destruction of grains and pristine material. In the subsequent phase, which you can by now spectacularly image with the Atacama Large Millimeter Array in Chile, the ordering of ice lines gives more structure to the disk. Here we see the gas disk in temperature and density in red and blue, and indicated are the two most dominant ice lines, the water snow line and the CO ice line. Outside of each, the respective volatile is in solid form. Inside, it is in gas phase. Pebbles, which are coagulated dust grains that settle onto the midplane, stream inward toward the protostar due to aerodynamic drag from the surrounding gas and transport volatiles from the outside to the inside. The successive stages of gas phase and solid phase chemistry, coagulation and drift, change the structure and radial ordering of important volatiles, as here illustrated with the ratios of CO and N to O in the gas and solid, relative to the ratio in the Sun. The competition concurrent evolution of dust grain growth settling to the midplane and gas and ice chemistry, as illustrated in these videos here, make protoplanetary disks very dynamic entities that are still poorly understood. On the left, we see disk scale height versus dust grain size in the evolution of the ice fraction grains versus gas volatile fraction, which is interconnected. On the right, we see how the main carbon carrier across the disk and with height can change by orders of magnitude over time. But these still do not ultimately define the composition of forming planets, as the formation journey from grain sizes to fully fledged planets is long indeed. At about a few centimeter in size scale, grains across the disk encounter several barriers, here illustrated by laboratory experiments, the bouncing and fragmentation barriers on the left, and the radial drift barrier on the right. Both of these barriers are related to the drift speed of grains. If the encounter velocities of grains become too high, the grains stop growing and rather fragment. This may stop planet formation. Connected to this, larger grains or pebbles on the order of a few centimeters start to decouple from the ambient disk gas flow and rapidly spiral toward the central star. Large grains can drift toward the star on a timescale of only a few hundred to a few thousand years, which is also a major barrier to further planetary growth. A leading contester to overcome these barriers is the so-called streaming instability, which is an interconnected back reaction between dense dust clouds in the disk and the ambient gas, which can lead to rapid gravitational collapse when the local dust density in the disk is high enough. This is illustrated in the computer simulation to the right, where you see the clumping of dense dust clouds that collapse to form burst planetesimals at specific locations in the disk with elevated solid densities. The outcome of this is in particular the size-frequency distribution of these burst planetesimals, the earliest larger bodies that build the seeds of the subsequent planetary accretion process, remains strongly debated. Estimates range from a few hundred meters to about 1,000 kilometers in size. Recently, however, some studies seem to converge on a characteristic birth mass with a steep turnover at about 100 kilometers in size. Now, I said in order to trigger the streaming instability, we require elevated solid densities. This means planetesimal formation may not happen throughout the whole disk, but rather at specific orbital locations. An often debated location that may provide a reasonable environment to do this is the water snow line. Inside of the snow line, water is in gas phase. Outside, it is in solid form, and therefore the solid density in general is enhanced in the outer disk. Because of the aforementioned particle drift toward the protostar, particles drift through the snow line where the water ice component sublimates. This decreases the particle size. It reduces the drift velocity, which leads to a pileup of particles at the location of the snow line, similar to a traffic jam. The buildup of this effect in disks takes on the order of 100,000 years or longer, but can create large solid overdensities, which makes the snow line an ideal location for the onset of the streaming instability. Another effect that may make the snow line the prime location for the onset of planetesimal formation is the cold finger effect. Water vapor diffuses from the inside to the outside of the snow line and subsequently freezes onto icy grains. This again enhances the solid density and can lead to planetesimal formation. This is faster compared to the traffic jam effect, but also less effective. In a combined model of the disk evolution from the onset of protostar accretion, here called class 1 phase, to the later disk stage, the subsequent triggering of planetesimal formation through the streaming instability by the cold finger and traffic jam effects can create two distinct stages of planetesimal formation along the drifting water snow line during the thermal evolution of the disk. I will come back to the possible compositional consequences of such a scenario later during the talk. Earlier I said that for the purpose of this talk I subdivide the accretion process in two stages, an early stage and a late stage. Interestingly, we have increasing evidence that the early stage that I refer to here really starts early, meaning during the inflow stage of the protostar and disk system. This is shown here on this plot, measuring dust masses in grains in ALMA disks over time, from disk class 0 to 1 to 2, compared to the total masses in exoplanets. This seems to indicate that the dust mass budget in class 2, that means late stage disks, is not sufficient anymore to build the observed exoplanet population. Therefore, planet formation seems to start earlier. This trend is corroborated by radiometric dating of the onset of planet formation in the early solar system. Iron meteorites indicate the formation of the earliest planetesimals only a few 100,000 years after CAIs. How do we know this? The ages of these meteorites are derived from hafnium-tungsten radiometric dating. This works as illustrated here at the bottom left. An initially homogeneous planetesimal has a specific ratio of iron and radioactive hafnium. The latter decays to tungsten with a half-life of about 9 million years. Tungsten is siderophile, which means it chemically binds to iron, but hafnium is not. If the core of this planetesimal now forms early, the hafnium stays in the planetesimal mantle and decays there. We later measure the core of this planetesimal in the form of an iron meteorite, which then would indicate a tungsten depletion. In the other case of late core formation, hafnium decays to tungsten before the iron core forms. In this case, the tungsten goes into the core together with the iron. In such a case, we later measure tungsten excess in such an iron meteorite. These trends enable geochemists to date the process of core formation on such earliest planetesimals. But how do cores form at all in a mechanistic sense? For iron and rock to separate from one another, the planetesimal must be heated such that the metal phases in the initially homogeneous mixed material can overcome friction and separate from one another. This requires a lot of heat to either melt the available iron or the rock phases to a liquid and decrease friction. In the earliest planetesimals, which were too small for gravitational potential energy to play a significant role, this heat came from the radioactive decay of another short-lived radioisotope, aluminum-26. As shown here on the left side, this isotope decayed with a half-life of about 700,000 years and contributed strongly to heating the primitive planetesimals and planetary building blocks up to the point of rock melting and iron core formation. On the right, you see a computational simulation of this heat-up and melting process. On the left, a thermal phase space and formation time which scales with heat output from aluminum-26 and planetesimal radius. Heating in these bodies can be so energetic that primordial volatiles are dislocated and degassed from initial cometary composition, and the aforementioned metal phases can separate from the primitive rock matrix. The isolines indicated on the left correspond to the sketches on the right, which illustrate the resulting hydrothermal activity and degassing from such bodies, and the formation of iron cores by separation of metal and rock due to either percolation, while the rock is still solid, or metal droplet rainout in internal magma oceans once the whole of the planetesimal body becomes liquid magma. These compositional trends with time and heating span the parameter space for planetesimals and are related to the retention or loss of volatile ices, here on the left illustrated for water ice, and the aforementioned metal cores on these planetesimals, as shown on the right. In general, large and early formed bodies become hotter due to strong radiogenic heating and lose volatiles quicker and differentiate to a greater degree. Later formed bodies remain colder and more pristine. In the early solar system, these trends build up a chronology of accretion in the inner and outer solar system, as shown in this plot. Here, I relate the timeline from radiometric dating using hafnium-tungsten radiochronology for core formation and other radiometric systems for water-rock reactions to the compositional scenarios from before. The red dots with uncertainties correspond to the inner solar system, called non-carbonaceous reservoir. The outer solar system is shown in blue, called carbonaceous reservoir. In the context of the scenario with the two planetesimal reservoirs that are formed due to the movement of water snowline and the triggering of two distinct episodes of planetesimal formation, the thermal evolution of the planetesimals acts to build up compositional differences between these planetary populations. On the left, you see the formation of metal cores in these planetesimals. Red and blue from left to right correspond to each other. The x-axis shows the time after CAIs, the y-axis shows the fractional amount of differentiated material of reservoir 1 versus reservoir 2. Because of the difference in formation time, and hence radiogenic heating, the red reservoir 1 builds cores early, while blue reservoir 2 builds them late. This can reproduce the clustering of iron core ages from meteorites that we observe in the NC and CC solar system record. The same for water-rock reaction, or aqueous alterations. Reservoir 1 experiences an early interval of water-rock reaction, but degasses and dehydrates quickly. Reservoir 2 experiences prolonged hydrothermal activity that can be measured today in meteorites. The timelines from the simulation here again reproduce the ages as found in the meteorite record. The competing, more classical model of solar system chronology has a long-standing tradition in the planet formation and planetary science community. Here, the solar system structure and successive episodes are interpreted in the context of an early formed Jupiter core, whose gravitational influence on both the planetesimals and gas in the disk shapes the dynamics in successive accretion of inner and outer solar system. In the upcoming time, we will need to explore how these different scenarios to explain the solar system architecture and compositional inventory may relate to one another. Let us come back to this sketch here. So far I focused on the early accretion stage, much of which is dominated or strongly influenced by the geophysical evolution induced by aluminum-26 decay. The end phase of accretion, however, is dominated by the gravitational potential energy from accretion itself. Bodies about the size of Mars and larger that accrete within the disk lifetime become melted from the energy of accretion alone. Similarly, like for the early formation timescale, we have radiometric evidence for the solar system planets that can help us to constrain physical mechanisms of accretion. The combined evidence from radiometric chronometers in this case provides evidence for the prolonged accretion of the proto-Earth within a time frame of a few tens of millions of years, with the moon forming impact, the last major accretionary giant impact, in a time window somewhere between 50 to 150 million years after the formation of the solar system. The dynamical scenarios during the final stages of the disk and the impact of a migrating Jupiter on the present-day architecture of the solar system has been a centerpiece of effort in the planet formation community in the last decades. This sketch here illustrates three major dynamical scenarios, which are not necessarily mutually exclusive, that aim to explain key features, such as the small mass of Mars, a Mars-depleted asteroid belt region, and water delivery to an initially dry inner solar system by scattering. The Grand Text scenario does this by inward then outward migration of Jupiter and Saturn in resonance, and outward scattering of inner solar system S-type asteroids to the asteroid belt. In the middle scenario, the asteroid belt is primordially mass depleted, potentially by local planetesimal formation, as I explained earlier, and subsequent outside-in scattering of icy outer solar system C-type materials. In the third, early instability scenario, the gas giants scatter S-types to the inside during the disk phase, followed by an dynamical instability of the ice giants that excites and mixes the asteroid belt objects to the present-day setup. The timescales in succession of the growth stages have become more diffuse in the last 5 to 10 years due to the novel model of pebble accretion. The more classical scenario of planetary growth works via successive accretionary impacts between planetesimals and embryos that grow the planets. However, with the growing evidence for millimeter-sized particles observed on disks, it seems likely that these particles themselves contribute to planetary growth after the embryos grow massive enough to attract these pebbles and coagulated dust grains gravitationally. The potentially diverging scenarios for planetary growth of gas giant planets and Earth-like rocky planets are illustrated on the right, where after the dust coagulation phase and subsequent planetesimal formation stage, planetary masses may bifurcate based on the local and temporal availability of pebbles. The consequences of the relative influence of these two accretion mechanisms can be critical, for instance for the formation of super-Earth. This plot here, for instance, demonstrates how in the classical collisional scenario the mass ratios of super-Earths can be explained by pure local accretion gravitational dynamics after the disk phase. This plot here, on the other hand, argues that the orbital dynamics and mean sizes of super-Earth planets versus terrestrial ones may be explained in the pebble accretion scenario. Apart from growth timescales, the influence of the growth mode on the volatile abundance of planets may be crucial. To refresh the memory, this plot illustrates how few water the Earth has compared to the outer icy moons. But if planets mainly grow from a succession of streaming instability beyond the snowline, pebble accretion, and rapid inward migration, then rocky planets may be expected to feature large water ice inventories. Another risk of drowning nascent rocky planets is pebble snow. During the evolution of the disk, illustrated off the right from top to bottom, the snow line moves inwards and reaches the terrestrial planet regime during late stages. If at this point icy pebbles are left over on the disk, they can pollute rocky protoplanets with large amounts of water during the final disk stages. Even if these mechanisms are not operating, classical inward scattering of planetesimals from icy regions by giant planets, or purely by collisional transfer from the outside in, may dislocate much more water and other volatile ices from the outer regions than we are used to in the solar system. This is because the volatile inventories of solar system building blocks are influenced by the radiogenic decay heating of aluminum-26, as explained earlier, and hence they are drier than compared to a system where aluminum-26 may be absent. This is likely the case for a substantial fraction of exoplanet systems that originate from low-mass star-forming regions. This plot here on the left shows the anticipated variability of radiogenic heating in planetary systems from intermediate to high-mass star-forming regions. This illustrates that the heating of planetary building blocks can insert order of magnitude degrees in ice abundances across planetary systems, and thus on the bulk water mass fraction of planets. On the right, you see a statistical evaluation of bulk water mass fractions that form in the classical scenario of planetary growth, subject to varying degrees of aluminum-26 heating. You see that with increasing aluminum heating, the water abundance decreases systematically because the accreting planetesimals become drier. Remembering the introductory slides, this order of magnitude decrease in bulk water mass fraction can induce substantial changes in the size of the ice carapace and hence rocky planet transit sizes. This is quantified here, comparing planet sizes in scenarios with and without aluminum-26 heating as contrasting end-member cases. This deviation may become testable with increasing numbers of known small exoplanets with missions such as the Extended Test Mission or Plato. For instance, the TRAPPIST-1 systems seem to feature a lower density compared to the terrestrial solar system planets. This may, for instance, indicate an ice-rich composition with a higher water mass fraction, or an oxygen-rich mantle with a small metal core and mantle mineralogy unknown from the solar system. Let me summarize the talk up to this point. These two sketches indicate qualitatively the main channels of volatile delivery and transfer during the accretion stage. Early grains may incorporate some volatiles directly from the disk due to adsorption onto grains, which I did not discuss further here, but may build up initial early volatile reservoir and planetesimals inside any ice lines. During the disk phase, water from the outer regions beyond the snow line can be transferred to inner regions by protoplanet migration, scattering, or collisional transfer, but the snowline itself may migrate and pollute inner regions early during the disk infall stage or later during final disk stages. If protoplanets grow to the size of Mars or beyond, they can gravitationally track the protoatmosphere of nebular gas. The relative efficiencies of these mechanisms set the stage for the final phase of protoplanet evolution that distinguishes habitable worlds from uninhabitable ones. Let's start this last part of the talk with the Big Bang. In this video, you see a cinematic illustration of the moon-forming giant impact, which vaporized and melted a large fraction of the Earth. The consequences of late-stage melting processes on the structure and compositional inventory of rocky and potentially habitable worlds are profound, and it is hard to overstate their influence. To start with, during giant impact events, planets can lose initially accreted volatiles by stripping primary volatile envelopes, which is illustrated in the left video. These calculations can be parameterized as indicated on the right in two recent versions. Qualitatively, these calculations suggest that high energy impacts during the last stages of accretion can substantially, but stochastically, reduce the volatile inventory of planets. To understand how magma oceans give rise to the earliest atmospheres of rocky planets, let us consider a recent, simplified version of the canonical story of the aftermath of the moon-forming giant impact, assuming that any prior primitive nebular atmosphere was already lost. Here you see the thermal evolution of the surface after cool down from the initial silicate vapor atmosphere. Surface temperature in red is above several thousand Kelvin. In this regime, the whole of the planet is completely molten. Most of its water is dissolved in the magma and does not contribute to the atmosphere substantially. The atmosphere is dominated by CO2. After the mantle mostly solidifies, the heat flow from the mantle does not stabilize the hot greenhouse atmosphere anymore, and the surface rapidly cools down. The water outgases in a short time interval and nearly immediately contributes to condensates in the cooling atmosphere and rains out to form the earliest oceans. The result of this is a potentially habitable planet with a hydrosphere only a few million years after the first hellish, completely molten magma ocean phase. Generally, the transition from primordial atmosphere to secondary outgassed atmospheres involves a variety of complex interacting processes, as illustrated on this sketch. The primordial H2 atmosphere captured from the disk interacts with the magma ocean. Parts of it will be dissolved in the mantle and be shielded from atmospheric escape. Depending on the hydrogen content and abundance of other greenhouse active species, the planet may be able to lose its hydrogen atmosphere, solidify, and establish a so-called secondary atmosphere with higher molecular weight species. This transition, however, and the timescales and importance of interactions between liquid mantle and outgassing atmospheres are poorly understood. One of the main uncertainties arises from the abundance of metals in the planet. On the left-hand side, we see the stripping of a protoplanetary mantle that creates a large core mass fraction, which is, for example, a leading theory to explain the large core of Mercury. However, during accretionary impacts, the degree of mixing between the cores of protoplanets and the dissolution of the iron in the resulting planetary mantle are unclear. For instance, large impactor cores may directly merge with the main planetary core, but smaller impactors may emulsify with the planetary mantle. It can therefore better chemically react and equilibrate with the rest of the planetary mantle. This influences the composition of mantle and the outcast atmosphere to first order. The reason for why this is important is shown here. In this simplified illustration, there are three reservoirs: core, mantle, and atmosphere. Pure metal phases, like iron or Fe0, which are chemically not bound to the rock, will segregate to the core. However, some volatiles that are in principle free can outgas to establish an atmosphere, are dissolved in the mantle while it is molten. Picture degassing CO2 bubbles in a bottle of mineral water. These volatiles, in particular carbon, hydrogen, and nitrogen, can in specific settings become very siderophile. This means that a substantial fraction of these volatiles that could in principle contribute to the atmosphere will instead chemically bind to the iron metal that rains out and merges with the core. This means these volatiles become sequestered in the core and are lost from the mantle atmosphere system, likely forever. A large portion of the hydrogen content of Earth may, for instance, be sequestered in its core. Measured in 8 atoms, The core may be the largest inventory of water in the planet. To complicate things further, the amount of free iron is not just set by any contribution from another impactor core merger, but the mantle mineralogy itself evolves during accretion. This is illustrated on the right side and governed by the equilibrium on the top left. Above a certain pressure in the mantle, so-called ferrous-iron phases, for instance in silicate melts, disproportionate to ferric iron, which creates perovskite. This reaction releases free iron metal that is unbound from the ambient silicate melt and will precipitate and merge with the metal core of the planet. You probably ask yourself by now why I carry these seemingly complicated processes to excess here. Well, this is because the composition of the mantle, which is measured in petrology and geochemistry, in terms of the so-called redox state, is the primary control on the speciation of the atmosphere that is in equilibrium with the magma ocean, and therefore determines the climate of young planets after they solidified following planetary accretion. All else being equal, a higher redox state, think more oxygen or water, or a larger planet with a deeper and higher pressure mantle, are more oxidized. These planets outgas atmospheres that are rich in water and carbon dioxide, like the Earth today. On the other end of the spectrum, reduced planets which are small or feature a larger amount of iron or hydrogen in their mantles tend to outgas hydrogen-dominated species, such as H2, CH4 or CO. This plot synthesizes how a variety of the mechanisms that I have discussed so far can work together to create fractionation effects between life-essential and greenhouse-sensitive elements. 4 scenarios are shown showing the fractionation pattern between H, N, C, and S as a result of different accretion and processing chronologies possible for the early Earth. The y-axis shows abundance in the mantle plus atmosphere without the core relative to Ci carbonaceous chondrites, the most primitive meteorites that we know of. The thick red line shows the abundance as measured in the present-day bulk silicate Earth, and the differently colored lines show the degree of metal-silicate equilibration in the aftermath of the moon-forming impact. You see how the effects of core formation plus atmospheric loss, and a late accretion of impactors that are either oxidized or in volatile rich, or reduced and volatile poor, can create order of magnitude deviations between these scenarios. But can we circumvent this whole dilemma? Perhaps magma oceans are not that prevalent in the universe, and therefore we can avoid dealing with these uncertainties and consequences. This is unlikely, as shown on this plot. It illustrates the occurrence of magma oceans in orbital distance versus time of the planetary system formation space. Internal energy sources that generate magma oceans are abundant in both time and space and substantially alter the fractionation, structure, and inventory of rocky planets. This ranges from aluminum and accretionary heating during the primary accretion phase to surface magma oceans induced by high irradiation on ultra-short period exoplanets, over induction and tidal heating, and eventually long-lived radioactivity, which may sustain internal magma oceans over billions of years. For example, Venus may still host an internal magma ocean today. What do we do with this knowledge? Is there any hope we can probe these interconnected mechanisms that so profoundly seem to shape young, potentially habitable planets? Yes, as shown on this slide, for the simplified case of a primary magma ocean that is dominated by water alone. The plot shows orbital distance, which translates to stellar radiation, versus final water inventory and solidification time for Earth-sized magma ocean planets with a predefined initial inventory of water, and only water. Under these conditions, planets beyond a certain critical distance evolve in the Earth-like fashion. They do not lose their water and can cool down to clement conditions within a few million years. However, at higher installation or on closer orbits, the same planet loses most of its water and becomes bone dry. The reason for this is the higher installation, which leaves the planet in a hothouse state for far longer, potentially up to billions of years. The water in this case breaks down due to photolysis in the upper atmosphere, and the resulting hydrogen is lost to space quickly. This is one theoretical explanation for why Venus today is the hellish place we know, and Earth is a habitable world. It indicates a direct prediction for exoplanet studies. Planets under high installation should experience long-lived magma ocean phases and may desiccate. Planets under lower installation may solidify and possibly form habitable hydrospheres if they are not swamped by primordial excess delivery of water. These effects become more complicated with more realistic and comprehensive treatments of planetary and atmospheric composition and state, as shown here for the combined effects of water and CO2. Adjusting this for additional potentially important species reveals that each species on its own can induce different equilibrium states, as shown in the right plot here. This distinguishes planets according to composition, size, irradiation, structure, and connects their present-day atmospheric states to their accretionary history. Before I conclude, let me highlight this plot, which quantifies our chances to directly image magma ocean planets in the future with ground-based or space-based astronomical facilities. Catching the afterglow from formation on these young distant worlds would enable a glimpse of their atmosphere and thus volatile composition. This plot compares two facilities: the ground-based extremely large telescope that is currently being built in Chile and a potential future space-based telescope, the Large Interferometer for Exoplanets, which will aim to observe Earth-sized planets in temperate orbits around other stars in mid-infrared wavelength. Such observations will eventually connect the volatile delivery and path during accretion with the climate of young planets. This can inform the origins of life community, or the viability of proposed surface states, and the climate of early Earth. It enables observational tests for specific environmental scenarios that can help refine our understanding of the volatile inventory, surface, and climate of the Hadean Earth. With that, let me summarize. We explore the various stages and mechanisms of volatile delivery during planetary accretion, which shapes the relative ratios of rock to metal to volatiles. On the continuous journey from star to planetary formation, the geophysics of accreting protoplanets shape the structure and composition of fully fledged planets to first order. Therefore, they determine the subsequent evolution and propensity to evolve to a habitable state. The continued exploration of solar system planet formation and the laboratory studies on extraterrestrial materials will help us to crucially constrain geologic and geochemical features that shape the interconnected core mantle atmosphere system of potentially habitable worlds. In the years to come, extrasolar planets will serve to help us refine our understanding of these processes that shape habitable planets from their inception to their long-term evolution, and will reveal bizarre landscapes and climates that will truly surprise us. With this, I would like to thank the Habitable Worlds organizers for giving me the chance to present this tour de force of planetary accretion and early evolution. To connect this talk with the virtual discussion rounds, let me highlight two questions that directly arise from the lines of thinking that are presented here. Where is the boundary between molten and solid exoplanets, and does it matter? And what are the primary compositions of temperate planets? Are they rocky, or rather big comets? Thank you very much for your attention and time.